Okay, so we'll begin this lecture today with a correction that we had discussed last time, and it's already been updated in the notes and mentioned, I think, on the email. And that's this matrix C, I think, was incorrectly written down. I believe there was perhaps a negative sign left off there. But anyway, this is the group of 6 elements. We want to show this as a group. We want to construct its Cayley table. So again, we've already seen that our 3-element group is just the identity matrix and that matrix B that has 0, 1 in the top row and negative 1s in the bottom row. And then D is sort of, we flip a little bit, the top row is negative 1s across, and then 1, 0 is in the bottom row. A has 0, 1, 1, 0 in it. C has negative 1 across the top row, but it's got a 0 in the first, and 0, 1 in the bottom row. And K, as you can see, has 1, 0 across the top row and negative 1s in the bottom row. And I think we were trying to show why it's closed, and that was where I ran into some trouble. So let's look at B times C was the calculation I made. So what we'll do is, you take this, if you think about what this is going to do, this top row here, when I multiply, is just going to produce the bottom row of C. So let's show maybe at least some of the details here in the beginning. 0, 1, negative 1, negative 1, and then C is negative 1, negative 1, 1, 0. And so that would give us 0 times negative 1 plus 1 times 0, and 0 times negative 1 plus 1 times 1. And so the top row is just going to be 0, 1. As I said, it would just be picks off the bottom row here. And then this would be negative 1 times negative 1 plus negative 1 times 0, negative 1 times negative 1 plus negative 1 times 1. And so that would then give us a positive 1 there. And this would give us a positive 1 minus 1 is 0 there, which is A. And how it would be different, so let me see if I can avoid taking all the steps here. So if I multiply these two, it would be negative 1 times 0. Negative 1 times negative 1 would give us a positive 1. And then negative 1 times negative 1 would give us a negative 1. 1 times negative 1 times negative 1 would give us a positive 1. So negative 1 plus 1 would give us a 0. And then this would be negative 1, which is that one of our matrices? That is K. And so we can go out and we can construct the Cayley table that's in your notes, based on all of these elements here. And we'll see that it is closed. So anyway, that was the mistake here, I believe, was the matrix C was incorrectly given. That should be as it is there and on the corrected notes. And so this group is not abelian, we can see that. So that gives us an example that's our first example of a finite group that is not abelian. Now we can make a few more calculations to look at one thing that's interesting. So what about the inverses? We can check for the inverses. We already saw that the inverse of B is D. And so D inverse is B. We went through that, I believe, earlier when we first introduced the group of I, D, and B. It was a 3-element group, and this was its own inverse. So those were the inverses of it. What about the inverse of A? Well, certainly, let's see what we have. Let's just do A times A So that would, again, this 0, 1 will have the effect of picking up when it's on the left. The top row of 0, 1 of a matrix on the left picks off the bottom row here and makes it the top row. So again, 0 times 0, 1 times 1 is 1, 0 times 0, 0 times 1 is 0, and 0. And then here, having the 0, 1 in the bottom row will pick off the top row here and put it down here. And you can do that. 0 times 1 is 0, 1 times 0 times 1 is also 0, so 0 plus 0. 1 times 1 is 1, plus 0. And so that means that A inverse is equal to A, right? Because A times A gives you the identity matrix. What about B? B we've gotten. D, what about D inverse? That's covered. How about C? Well, there's not much left, right? Inverses are unique. Either C and K are inverses, or maybe C is its own inverse. Let's see. Why don't we do C times K? And so since these matrices are written up here, this top row would be -1 plus 1, so that should give us 0. And then 0 plus 1 here. And then here, having this as the bottom row would just pick off the bottom row here. We should get -1, -1. And 0 times 1 is 0, minus 1 is a -1, so that goes in this slot. And then 0 times 0 is still 0, and -1 in there. And that's one of our matrix. That looks like it's B. So certainly the inverse of C is not going to be K. Let's make sure I've got this in the Cayley table right. So I'm looking at my notes here. I see that C times K is B, so I had that correctly. So what is the inverse? So let me erase the board in a moment, and we shall see. I think if we square it, we should get C squared would take us to the identity matrix, and the same with K squared. And let me run through that calculation. And then you can also see that if you look at the Cayley table that I produced in the notes. So let's look at C squared. And we'll get a +1 plus 0, so a +1. And a +1 minus 1, 0. And then this, as I've said a few times, right, if we have 0, 1 on the left, in a 2x2 matrix, I'll pick off the bottom row. Put it here, and sure enough, 0 times -1 is 0, plus 0 is 0, and 0 times -1 plus 1 times 1 is 0 plus 1 is just 1, the identity. So C is its own inverse. And same with K. K, I believe, was this matrix. So this takes off the top row, and then this would give us a 0, 1, -1, plus 1 is 0, and negative 0 times -1 is 0, plus 1 is just 1. So K is its own inverse. So we've shown the inverse property, and the closure, we haven't completely shown it, but you can look through and verify those Cayley table calculations. And we see that's an example of a non-abelian group. It's not equivalent. So let's look, it's not abelian, as that example showed, where I think we did C. Once I finally corrected the typo, we saw that K, what is it, B times C, and B times D, B times C was different than C times B. And I think in the notes I've even given another example, A times B and BA. So I've gotten a few examples, and a few of these calculations are in the notes. So let's now introduce a different group of 6 elements, but is it really different? One thing you might notice, those 3 elements, C, K, and A, they were both their own inverses. If you applied them twice, they gave you the identity. So what's something else that is, if you do it twice, it takes you back to where you started? A reflection, right? If you reflect something and then followed by that same reflection, you get the identity composition. So that's really what I see. These matrices are just a different way of representing a very important group. So what we have here is just that group A, C, B, so we look at the symmetries of an equilateral triangle. And I try to indicate in the note, one way of trying to describe these symmetries is we can take a matrix, take an equilateral triangle, consider it labeled like that in standard position, so A at the top, and then B at sort of the bottom right, and C at the bottom left point of an equilateral triangle. And we can almost describe a symmetry by the resultant position we have. So what are some of the symmetries? So a symmetry is something that leaves the figure unchanged, and there's really not too many about them. What are the symmetries? There's 3 reflections, and we'll maybe look at them in specific views, but if you draw an altitude from a vertex perpendicular to the side opposite it, if you use that line of the reflection, that would be a symmetry. And the other reflection wouldn't give you a symmetry if it's not going through a vertex and it's the perpendicular line. This is, again, from geometry, not only is this altitude, if we drop a perpendicular on an equilateral triangle, then in fact it's bisected. So it's not just a perpendicular, it's a perpendicular bisector. And then you could also, right about here, there's a center. What is the center? Well, again, appealing to some geometry, that center might be where all 3 of the perpendicular bisectors meet. And you could rotate. Well, there's actually 3 rotations. You can rotate by 120 degrees. Or you could rotate by 240, or you could rotate by 0 degrees. You could think of that as an identity transformation. So there are 3 rotations. I think that's called the circumcenter. Again, in geometry, that point that's where the center, a circle that goes through that circumcenter, and any one of the vertexes will actually go through all 3 of the vertexes in that. And we just have to think of 0 degrees as being a rotation. So sometimes it's convenient to think of, if you don't do anything to an object, imagine that as being a rotation by 0 degrees. And so what we want to do, so we want to look at these 3 symmetries. So there's 6 symmetries. of transformation. So let's look at that. Is it a group? And let's just try to go through describe what they are, and then go through the Cayley table, maybe even give these names. So first of all, is it associative? So if you think of a transformation, that's really a function composition. And as I mentioned in the note, function composition is by its very nature associative. Almost by its definition. So we'll show that, and that'll show that the action of composition of these geometric transformations is associative. And then we'll just go ahead and do the Cayley table. Okay, so I'll give you a moment just to look at this table. Remember, we'll run with A, B, C. And the rotations, we should also say rotations clockwise. So we'll consider, if we turn it like that way, 120 degrees, that would give you, that's what we'll consider by 120 degree rotation. So again, in a group, the way you multiply functions, the operation usually on functions is function composition. And so why is function composition associative? So y is, if we take f composed with g and compose it with h, equal to f composed with g and h. Well, how can you show a function is, or two functions are equal? You just take an arbitrary x and show they give you the same value for x. So if we look at f composed with g, composed with h, and we plug in f, that's f composed with g of h of x. But definition of f composed with g, so if you think of this as your function, one function composed with the second, that would just be f of g of h of x, right? Because that's how I would compose these two functions. I take this input value, h of x, I plug it into g, and I take that result and plug it into f. But I look at that and I say, wait a second, in this parentheses here, g of h of x, that's exactly what g composed with h is. But then if I have f of g of circle h of this, and I plug that into that function, that's really the same thing as f composed with this function. So I think I've done it, right? F circle g parentheses composed with h is the same thing as f composed with g composed with h in parentheses. So function, any function composition is associative. In particular, combining transformations, composing transformations will be associative. So what are the elements? So let's call E the identity. That's rotation by 0 degrees. And then maybe I can use a little bit different notation for my notes. I gave it a letter E. I think of that, maybe call it R sub 0. And certainly that's going to be the identity, right? If you take any geometric transformation and you follow it by doing nothing, that's the same as just doing that geometrical transformation. Or if you do nothing and then you hit that with a geometrical transformation, that's the same as just doing the geometrical transformation. And I think, then in the notes I used A for a rotation by 120 degrees. And again, some things we use R sub 120. Actually, I guess I used capital A. And in the notes I used capital B. That's a rotation by 240 degrees. And what I'll also do is also describe these by how they end up with the triangle. So here your triangle would just be the same, A, B, and C. So in a way you could think of E as just ending being with this. Then R of 120 you could think of ending with now if I rotate, the A would be here, B, and C. Again, these triangles are all equilateral, though they may not look it. And 240, if I took this and rotated 240 degrees, the A would be here, the B would be up there, and the C would be there. And then I also have some reflection. That's a reflection about and I believe that the term for the line, the altitude is a line from a vertex perpendicular to a side. The altitude through and well, let's make it through A. That would keep A the same, and that would flip B and C. And we call that capital C. And then we have what I call D. That's a reflection about the altitude through, I forgot, I said that's vertex A for C. D would be the reflection of the altitude through vertex B. So that would keep this one fixed, and that would switch A and C. And then finally, E. Well, actually, E sometimes gets confused with the identity, so I think I called it F. That's a reflection about the altitude through vertex C. So that would keep the C fixed, and that would switch B and A here. So you can really identify each of these 6 geometric transformations by how the labeled triangle added up. And the key with function composition, the way we'll define it, if we had to say A times B means, this is very important here, first B, then A. And again, we borrow that from function composition. We think A times b, if those are transformations, those are special types of function, that's really a composed with b, a circle b, and the way you define a circle b of an x would be a evaluated at b of x, so actually x goes into b first. So we do it that way. First b, then a. Okay, so let's do a Cayley table then. So we have the identity, I guess I use little e at least for the identity. A, B, C, D, E, F. And then E, A, B, C, D, F. And then this is in the notes, and I'm not sure I'm going to complete all of this table. But let's just work our way through this. Also, a good way to experiment with these, if you cut out a triangle with cardstock and label on the front and back allows A on each side, C and B on each of the vertex, that can also be useful. So I'm not going to take the time here to clear what these two rows should be. What about A squared? Well, if we take this, turn it once, we'd be here. If I turn this once, it would end up with A, B, C. So A squared would be, so turn it once, then turn this another 120 degrees, A, B, C. That's this one right there. That would be B. So A squared would be B. Again, just imagine, take this triangle, how would it end up? You would turn this once, it would look like that. Turn it again, you would end up with, this now would be A would go here, the B would go here, and the C would go there. And you say, oh, wait a second, that's a rotation by 240. Again, it makes sense from rotation, right? If you rotate by 120 twice, that's the same as rotating by 240. What about AB? So let me begin to maybe erase some of this material here. So let me at least rewrite the code. So E, we can think about as being A, B, C. A would be A, B, C. B, so I'm just copying over what I've written there. A, B, C like that. D, that was a reflection through A, so that would be A, C, B. I'm sorry, that would be C. D, we left this the same, and that would be A, C. And finally, F, the C remained in the lower left corner, and these two switched. So what about AB? So we take our triangle, if we do B first, that would be a rotation by 240. So that would take us to a triangle that was labeled A, B, C. And then if I hit that up with B, that's another 110 degree, that would be A, B, C. So the net effect of doing A and B, it's as if I've done nothing, so I would just get E, the identity. Then you can run through that, and that makes sense, right? If you rotate by 240 and then rotate by 120, it's a total rotation of 360. That's the same as a rotation of 0. So that entry, that B first, then A, if I do A first and then B, that would also give us the identity. So we fill that in. Yeah, I will show that, but that you could also go rotate by 120 and then rotate by 240. It's a net result of a rotation by 360, which is the identity. So again, what we want to do is we sort of take our triangle in the original position, we do one or more of these transformations, and we see which one it results. So what else should we multiply? I guess A times C. Which again means do C first. So after doing C, our triangle will then be a reflection through this point A. So that would be ACB. Then we hit that by A, that would be a 120 degree rotation. So the A would move down here, C and B. And so the net effect, if I do C, AC, which is first C, then A, that's the same thing as which one? I look which one had A, B, A, C, B, A, C. That is F. And again, in the Cayley table, the entry on the right goes here, so C times A would be F. And we see that's indeed what I've gotten in the Cayley table. What about the other way? What about A times C? So if I do A first, that would be this rotation. Then if I follow that by C, C would be reflect around this thing, so this B would stay fixed. And those two here, I get A, C, B. And that is the one, let's see, let's see, is that right? Let's see, so I do A, that would initially A, B, C, and then I would have to do C. C would be fix this one. Oh, I'm sorry, C fixes this one. So right, B, should be pointed out those vertex are starting from the initial position. So C, think about, is we'll fix the vertex at the very tip, the top. Transformation D will always fix the vertex at the bottom right. F will always fix the vertex at the bottom left. So that's the vertex that you use to draw your altitude. So this would now be fixed as C, and these two would slip, so we'd have A and C. So we'd have C, A, B. And so we look around for C, A, B. And CAB, so that would be that would actually be C, right? C flips the C fixes this, so that should be D. Okay, so I guess I've mislabeled D here. Luckily that hasn't come up. D, remember we fixed D was the one that fixed this vertex right here, B, and we'll switch these two. So this would be C, A. So that would be D. We'll fix this B, so that would be A here, and C here. So C, B, A. Then F was the one that fixed this lower left vertex. So that would be that one there. So what do we get? So CA, I have, according to my notes here, CA should be D. So again, CA would be A first. So if I rotate first, that would give me A, B, C. And then if I apply A to, I do A first. Then if I apply C to that, C is the one that fixed this one. So it should switch these two. And I should get A and B would swap, so C, B, A. So what's the net effect to take the original position triangle and put it at one like that? And we see that is exactly D. Okay, so sorry about that. That was in the mislabeling. Again, let's just go through that. A, we twist it. We rotate clockwise 120 degrees. Then we reflect through the top vertex. That has the same net effect as if we took the original triangle, ABC, and we just flipped through these two ones, and that's CBA. Okay, so in view of that, maybe we ought to do a few more calculations. So what else? AD, have we done that one yet? So AD, again, we do D first. So in the original ABC triangle, that would fix this one and switch these two. Then A would rotate it 120 degrees, so that would be a C, a B, and an A. So net effect to take an original triangle and go with A, C, B, you can see that's keeping this top vertex fixed and reflecting about its altitude. So that would be the one we call C. So A first, A on the left, D on the right would give us C. And DA, oh, we just did DA. AD, or no, DA, I said it, right. We do A first, that would rotate 120 degrees there. And then D is the reflection through the bottom right vertex, so that would flip those two. And so that would give us a B, C, and an A. And so the net effect, BAC, is F. So D on the left, A on the right would be an F. And so we can always see how the groups are not abelian, right? These different ones. So again, I think I've gotten the Cayley table right. Let me maybe do maybe D times E, or E. There is no E. Right? 1, 2, 3, 4, 5, 6. Right. A, B, C, D, F, and E we've used for the identity. So AF, the only thing it could be, this is identity, so A, B, F. The only thing that doesn't appear would have to be D. So that's what it should be to be a Cayley table. Let's just check that that's indeed the case. A times F will give us D. And so that means doing F first. F fixes this lower left vertex C and switches B and A. And then A would rotate 120 degrees, B, A, C. So we end up with C, B, A. That's D, that we knew it had to be. And lastly, let's try two of these, D's and F's. Why don't we try, I don't know, D times F. So we do F first. As before, that would give us C, A, B. And then we do D, which is, fixes this, so that would fix this. and we'll flip those to dA. And so what's the net effect of F on the left, F on the right, D on the F on the left would be what? A, let's see, D, is that right? D, that's the same thing. So D would reflect, so I've done F, which is fix this one. Then I have to flip these two, so that would be B, C would be A, B, C. So that looks like a 120-degree rotation, just A. And if you look in the notes on the Cayley table, D times F is A. And you think a little bit from geometry, maybe if you reflect once and then you reflect again, that has a net effect of being a rotation. Right? Generally in a rotation you wouldn't reverse the direction of something, so reflect, you reverse the direction, reflect again, you reverse it back to the original direction. So that's why it makes sense that compositions of these reflections should give us a rotation. So we can just finish up the table. You can go through in the notes. Again, it's a really good idea if you try to get a piece of cardboard stock, something a little sturdy, draw a triangle and label it, and then just actually physically do the geometric operations and see what the net effect is. Okay, so we have that. And I believe we've shown cancellation unique, so we're almost done with the group, the various groups lecture. Just like to conclude with one of the things we talked about. We saw in the Cayley table for 4-element groups, there are actually 2 elements. There were 2 distinct groups, right? The one group we saw by getting the complex roots of unity, as they're called, or in particular, 1, -1, I, -I under multiplication of complex numbers was a group. But we saw there was a different group where every element squared was 1. Every element squared was the identity. So how can we build that group? So what we need is this following construction. It's a way of sort of taking 2 different groups and mashing them together to get a third group. Before I do that, let me just kind of, again, maybe we'll call this like bonus DVD material. It's not really in the notes yet, though we'll certainly come back to it later. But an equilateral triangle is a 3-gon in terms of a polygon. I think the term they use is regular. All the sides, lengths, and angles are equal. A regular 3-gon. A square is a regular 4-gon, 4 sides. So what about the symmetries of a square, which is a regular 4-gon, a regular polygon with 4 sides? Again, a regular polygon is a polygon where all the sides and all the interior angles have the same length. Is this a group under composition? how about the symmetries of a regular n-gon, a regular polygon with n sides? Is this a group? And then in each case, how many elements did we have? Again, with the 3-gon, the triangle, it looked like we had 6 elements in the group, 6 symmetries. 3 rotations, if we count the rotation to be 0 degrees to be a rotation, the identity transformation, and then 3 reflections. What about a square? How many rotations? How many reflections? Are there any other types of symmetry besides rotations and reflections? Anyway, we'll just come back to it, but I just wanted to get a little bit. This answer actually is yes in both cases. A square actually has 4 different rotations by 90, 180, 270, and 0. And it's also got 4 different reflections, depending on about which one is a vertical or horizontal, and then through the 2 diagonals. So there's a total, it is a group, and a total of 8 elements. And so you might think a regular polygon with n side, perhaps there is the symmetries of that also form a group of 2n elements. N reflections, and then n rotations, counting the do-nothing transformation as a rotation by 0 degrees. So we'll come back to that. But I'd like to conclude with a couple of things. The first is going to allow us to get a Cayley table with 2 different groups. And they'll give it a Cayley table, or use a way of creating a group from 2 different groups, and this will allow us to get an actual realization of the Cayley table for the 4-element group where every element is its own inverse. So, definition. Let A and B be sets. We define A cross B, the product of A and B, sometimes called the Cartesian product of A and B, as just all 2 ordered pairs, A and B, where A is an element of A, and B is an element of B. So that's the product of A and B. Sometimes it's called the outer product of those 2 groups, or sometimes it's just called the Cartesian product. Again, as a second example of this, the number line you can think about as being the real numbers, then the plane would be R cross R, is the 2-dimensional plane. You have 2 different number lines, and so all the points in the plane are really ordered pairs. Here, if A and B are groups, then A cross B is a group under the operation so what are 2 elements of it? A comma A prime comma B prime, and that would be A comma A prime, B comma B prime. For all A and A in A and A prime in A, for all B and B prime in B, where AB is the product in A, and B prime is the product in G. Oh, sorry, not in G, in the second group, B. So you may have two different operations. You know, maybe the first component you're adding things, the second component you're doing division or some other thing. So let's try to prove this. Remember, group is a non-empty set. So A has an identity and I'll just call it E sub A to indicate the identity of A. And B has an identity E sub B. So if I look at E sub A, the identity of A in the first spot, the identity of B in the first spot, that's certainly an element in the product of A and B. So A and B is not the empty set. And you have to appeal the identity. You know, if as groups A and B are not empty groups, so there's an element A and A, there's an element B and B because they're not empty. So therefore, A comma B would also be an element. So you didn't have to use the identity. It just shows something is in A and something is in B. Now let's show the identity property. So I need to erase this top thing. I mean, this is notes as well. But we'll more formally look at ways of representing these symmetries. So let's show the identity property. So for all A comma B in A cross B, if I look at that element I just discussed, EA times comma EB times AB, that equals EA times A, comma EB times B, but that's just A, comma B. And it certainly go the other way. Remember, EA and EB are two-sided identities. So if I multiply the ordered pair A, comma B on the right by the identity of A, comma the identity of B, a very similar thing would happen. So A cross B has an identity. What about an inverse? Let A inverse in A be the inverse of A. Kind of redundant, I guess. And B inverse the inverse, which is again, key is because A is a group, A inverse is in A, and since B is a group, for B and B, B inverse is in B. Then what's going to happen, then AB times A inverse B inverse is A times A inverse B times B inverse, which is just A times A inverse is the identity of A in the group A. B times B inverse is the identity in the group B. And also the equation, remember the assumption of a group, the property, the inverse property is a two-sided definition. So if I multiplied A comma B by A inverse comma B inverse on the left, that would still be okay because not only is A times A inverse equal to the identity, but A inverse times A is also the identity for A, and B inverse times B is also the identity for B. So we've got the identity property proved. So is there a group? Just summarize that. So if we look at A comma B, the inverse of that element is just A inverse comma B, which is an element of A cross B. So the inverse property is met. So do we have a group? Non-empty? Closure. What about closure? Have we talked about closure? Well, again, for all A comma B in A cross B, for all A prime comma B prime in A cross B, if we look at the product, we have A prime, B prime, but that's in A cross B since A and B are closed, so A and A prime are in A, so their product must be in A, since A is a group. And B prime are in B, so their product must also be in B, since it's a group. So how about associativity? So associativity, maybe I'll just use some numbers as subscript. So let's have for all A1, B1, A2, B2, A3, B3 that are in this product. So if those three ordered pairs are in the product, that just means A1, A2, A3 have to be in A, because the first component has to be in A, and B1, B2, B3 have to be in B. Then let's look at the product. So let's look at A comma B1, and let's multiply that, put the parentheses here, A2 comma B2 times A3 comma B3. So the parentheses is here, so I multiply within the parentheses so that A1, B1 stays the same. And and this becomes A2, A3, B2, B3, and I'll throw some parentheses in there. Why not? They're free until you put something in parentheses. Now let's multiply those. That's equal to A1 times, in parentheses, A2, A3, comma, B1, and in parentheses, B2 times B3. So what does that equal to? Well, now remember, A and B are groups. So they must meet the associative law. So now this multiplication here is within A. This multiplication is within B. I can slide those parentheses over. And I get A1, A2, in parentheses, times A3, and B1, B2, and in parentheses, B3. But here I have an element of A times another element of A in the first spot, an element of B times another element of B in the second spot. That's exactly the same as A1, A2, comma, B1, B2, times A3, B3. But again, within this parentheses, that's exactly the definition of A1, comma, B1 times A2, comma, B2. So I have that product, and then I take that, and this I'm just copying over. And I think if we untangle that, you see associativity holds. Now, you might point out in a lot of the examples, we kind of left the associative law. We appealed to the fact that we know matrix multiplication, or addition of integers, or addition of rational numbers, or something, multiplication of complex numbers is associative. Here we actually went out and proved the associativity. So again, let me quickly run through these equalities. That's what we set up. X, I don't want to use A and B for the group, so we can think of X, and then in parentheses, X times, or Y times Z. But here the definition of multiplication in A cross B would give me this. But again, I have something in A, comma, something in B. This is an element of A cross B. This is an element of A cross B. So the definition of multiplication would give me that. Then I have the associativity law in each individual component. So I use the associativity law in A and the associativity law in B to slide that parentheses over. But then I look at this as an element of A times another element of A, an element of B times another element of B. The definition of multiplication in A cross B would give me this. But again, focusing just on this element, the definition of multiplication A cross B would mean this element is equal to this product. So I have this product within a parentheses with this element here. And that's exactly the associativity. And so that completes the proof of the theorem, because we've shown the associativity and we've shown closure and we've shown the identity. And on the board I've just erased, we've shown the, that's actually the inverse up here on the board. We just erased, we showed the identity. And we also showed that it's not empty. And this is proven in the notes. I think in the notes, instead of using subscripts, I use different letters, A, comma, B, C, comma, D, E, comma, F. Usually you don't want to use E as a general element, because E would stand for the identity. But I guess over there, since the identity was E sub capital A for the identity of A, E sub capital B for the identity of B, it was okay just to use E as an element of A. So I'm just looking through my notes now, make sure I got the quantifier right there. So I probably should have even added that in the notes in some detail, where those elements are. I don't think I've actually said that. So I'll go back to, in the notes, in the lecture notes, I'll maybe update some more the minor change of where those elements are and why those hold. But I think I pretty much gave you the idea behind it in that proof. And then we're going to have a very useful theorem. This proof is a little bit tricky. I don't think it's ever the type of proof I would ask you to do maybe on an exam or something. But I'd like you to be able to apply this theorem. And it's actually two theorems. There's one I proved in the notes, and then there's a very similar other version of it that I'll prove something different today. So the theorem that I proved in the notes is let G be a group, let G be a set with a binary operation that is associative and for which there exists a E in G such that for all X in G XE is equal to X, and for all Y in G, there exists or let me just say, for all X, quantify for all X in G, there exists a Y in G with XY equals the identity, then G is a group. Well, why isn't this just a statement of fact? Well, if you remember, the properties of the identity and the inverse were two-sided. You were required to prove that you had both a right and a left identity. But this shows us if you have something we can maybe call this a right identity for any element, and then X has a right inverse to take you back to that right identity, then in fact you must have a two-sided identity and two-sided inverse. So in a homework problem or a test situation, if you're asked to prove something is a group directly from the axioms, it saves your calculation, right? If you can show you have an E that satisfies, it's an identity on the right-hand side, and you can show you also have a right-handed inverse for each element, that's enough to prove it's a group if you have all the other properties. This does not mean that every right identity, if you have a right identity, it's also got to be a left identity. You need this property as well. So it's very important that you need both. So just kind of in words, both right identity and right inverses for each element that means you in fact have a group. Or two-sided identity or two-sided inverse. So while this is a very good proof to follow and understand, it's a little tricky argument, but I think helps you understand proof techniques and also some of the structured group. the main use of it is that if you're asked to prove something is a group, you can cut down on the things you have to show, right? You don't have to show you have two-sided identity and two-sided inverses. You just have to show you have both a right identity and a right inverse. I don't think it works the other way. It does not work if you have a right inverse and each element would have a left identity. That's not what the theorem says. That doesn't guarantee you have a group. And there are lefties in the world, right? Well, what's so special about the righty? So I'm not going to prove this theorem. Hope I'll check. You can look through the notes, and hopefully I think they're detailed enough that you should be able to follow it. I'm going to prove the left-hand version of this today. So what that shows, if you have a set that meets all the properties of the group, if you've got left-sided inverses and left identity, both of those properties, then you have a two-sided group. So this is the actual theorem I'm going to prove. Let G be a, actually in that example I should have said a non-empty set. So you probably can't see that on videotape. That just says G not equal to the empty set. So non-empty set. So let G be a non-empty set with a associative binary operation and such that for all A and G, I'll switch the order. There exists an E in G such that E A is equal to A for all A and G. So again, that's why I call it a left identity. You multiply on the left. And 2 for all A and G, there exists a B in G with, again, we want to have in the notes I proved the right version of this, so I want to think about B as being a left inverse of A, so B on the left times A would take you back to identity, or the left identity. Then G is a group. So this is what I like to prove for you. So we've got a binary operation, so that's closed automatically. It's associative, so we have associativity. So to prove, we need only show there exists an E in G such that, well, let me just not be such that for all, I'll just use X and G, EX equals, oh no, we already know that by assumption. XE equals X. And for all X in G, there exists a Y in G such that, again, we know Y is going to be a right end. We know by assumption X has a left identity inverse, but in fact it has a right inverse. Okay, so let's take a look at this. So certainly E such that, well, actually, let me start off with take any x in G. There exists an E with x, or EX on the left by E equal to x. That's the first assumption. We want to show what? That XE is equal to x. Well, x has a F inverse, so let xy be the left inverse of x. That's guaranteed by condition 2. So yx equals E. Now let's multiply each side on the right, let's multiply each side on the right by E. So what does that get us? That gets us yxy equals EY. Let's see, we take that back. We have this equation, let's multiply on the right by E. So xye equals EE. Or if we slide these over, this becomes, here we don't really matter, the parentheses can put in either spot, so it becomes xye equals E. But E is just xy, so this becomes xye equals xy. I feel like we could keep the parentheses here. But I think, as I remarked the other day, sort of the associative law allows you to write A times B times C and not have to put a parentheses there. Okay, but what about Y? Y is an element of the group, so by assumption 2, Y has a left inverse Z with Z times Y equals E. So this becomes what? So this equation becomes, what I'm going to do is I'm going to multiply on the left by Z. So we would get zy times xe equals z times xy. But zy is e, so this becomes e xe equals, I'll move this parenthesis over, zyx, that's the associative law. But as just the line before, first of all, E times this element. E is a left identity, so this just becomes xe. And this z times y is E, so that would be EX. Or what does that now tell us? Well, E is a left identity, so EX is just X, so XE equals X. And so E is also a right identity. Since X was, maybe a term for it we can use as an arbitrary element of G, right? Nothing special about X. I took A, X, and G, and I can show that that left identity E has the property that it's also a right identity. XE is equal to X. Notice it's not enough. You can't just use the right identity property to prove it's a left identity. We also have to use the, so we can't just use the left identity property to prove that that is also a right identity. We need to use the inverse, the left inverse property a couple of times. Okay, now what's the other way? Now, for any X in G, let Y be the left inverse. So that would give us XY equals E. But let Z be as 4. Z is the right, Z is a left inverse of Y. So that would mean Z times Y is equal to the identity. Okay, so let me erase a little bit. But remember, we've already proven in this proof, we haven't completed the proof of the theorem, but we have proven that the left identity E is also a right identity. And so we're going to use that. So how will we use that? So we have let's take xy equals E. And let's multiply on which side do I want to multiply? I want to multiply on the first on the left let's see, what do I want to do? We have yx equals E. Let's multiply on the right, on the right by y. And that's to get yxy equals E y. Which is just the same as yxy equals y. So if we multiply on the left by z, the left inverse of y, zy xy is equal to zy. This zy is equal to E. So zy is E, so this becomes E xy equals E. But E is a right identity, so, sorry, E is a left, well, it's both a left and a right identity, so this becomes xy equals E, and y is a right inverse of x. So that completes the proof, right? I've shown that that completes showing that if I have y is the left inverse of x, y also has to be the right inverse of x. X times y also has to equal E. Okay, so that concludes on the proof of this. So the proof of the theorem is complete. And like I said, those proofs a little bit tricky how they left and right. It was not really, I think it's, you can memorize it, I can ask you on the exam, but it's more likely, the reason I've covered it, well, I think it's good to watch the proof being done, but the main reason I want to give this to you is this can shorten some of your calculations. If you want to prove something is a group, pick left or right, I don't care, pick one. Show that it has both a right inverse and also a right identity. That's sufficient to have a group. And the other thing I have left out, which I'll go back to, is we define the product group. So why the heck did I do that? That's to give an example of that 4-element group where every element is its own inverse. So let G equal -1 and +1 under multiplication. Then G cross G, we've already seen is a group. Where for all G and G cross G, G squared is the identity. So we can make the Cayley table. So what are the elements of G? 1, 1, 1, -1, -1, 1, -1, -1, 1, 1. I think I'm not going to have enough space, but we can maybe at least do some of these. -1, -1. Looks like I'll be missing a row. -1, comma 1. So I multiply each component. 1 times 1 is 1. 1 times 1 is 1. One times 1 is 1. 1 times -1 is -1. 1 times -1 is -1. 1 times 1 is 1. 1 times -1 is -1. So of course we get that same thing there. And this would be 1, -1. -1, 1. And then here, 1 times 1 is 1. -1 times -1 is 1, 1. So you see, an element times itself gives you the identity. 1, comma 1 is the identity. That's because in that group G, 1 is the identity in group G. So in G cross G, the identity of G, comma the identity of G would give you the identity element. Again, we can use this construction. Nothing said A and B couldn't be the same group. And then here, 1 times 1 is -1. -1 would give us that. And 1 times 1 would give us -1. -1 times -1 would give us +1. So you remember how we had the table? I think we had like A, B, C, D, and then the Cayley table, you know, would give the other element. This would be B, E, the identity, C, and then B. So this would give us -1, comma -1, 1, comma 1. Again, this element times itself gives us the identity, and then this would be a +1, and a -1 would give us that. Now I just have to do the bottom row. Would have a -1, comma -1, so this would be the very bottom row. And the top row, we've got all 4 of those covered. 1, 1, 1, -1, -1, 1, -1, comma -1. And so this would be, of course, times the identity, it's going to be itself. This is -1, +1. Which it should be, look at -1, +1. That's not in this column, which is good. Then this would give us +1, -1. So hopefully that's not here. See, +1, -1 is not in that column. Remember the Cayley table for a group, there cannot be any repeats across any row or across any column. And then lastly, this will give us +1, +1. Again, no repeat across this column. That's not among these 3 entries, so no repeats there. And this element times itself gives you the identity. So this group is sometimes called the Klein 4 group. It's a very famous, the 4-element group. It's abelian. Every element is its own inverse. And then I'll write this in the board again with that product group. If A and B are both abelian groups, then A cross B has to be abelian as well. So that's really a corollary of that earlier theorem. So if the groups A and B are commutative or abelian, then A cross B is abelian as well. And the proof of that is pretty simple. We've already proven it's a group, so suppose we have for all AB and A cross B and A prime, B prime, and A cross B. You can see what's going to happen, right? AB times A prime, B prime. Well, the way we multiply is by components. But if A and B are each abelian, A and A prime has to be that. B times B prime is the same as B prime times B, but that's exactly A prime B prime times A comma B. So that concludes the lecture on groups. And we will move on and start talking about subgroups next.